I'm going to discuss augmentation technologies for enhanced physical performance, and with that said, it's more of the wearable robotics, exoskeletons, human augmentation. There are many, many names for these types of devices. Quick background of NSRDEC. It's considered the soldier's RDEC, and we are located in Natick, Massachusetts. And this is a prime location due to its proximity to all the great universities and academic institutes in the Boston area. And on base, we also have partners of USAREUM, the United States Research Institute of Environmental Medicine, part of MedCom. We have the Coast Guard, we have the Navy, we also have the SOF community as well, all located at NATICK. It's one of the only, or actually, yeah, the only active Army installation in New England, so that's also unique. Some missionaries of NSRDEC, we have the Joint Service Combat Feeding, so all of the performance nutrition and the Joint Services food equipment is located at NATICK. We have the expeditionary basing and collective protection, so all of the sustainment systems that the Army uses goes through NATICK and developed at NATICK. We also have the airdrop and aerial delivery, working on resupply systems and everything that has to do with the airdrop. And I'm part of the Human Sciences branch. I'm the biomechanics team leader, and we have the human factors, the biomechanics, the anthropology team, as well as the cognitive science team, all housed in the human sciences. And within the Warfighter Protection Directorate, we also have the development of the clothing and individual equipment, body armor, helmets, boots, you name it, anything the soldier wears or uses to protect himself at one point goes through NATICK. And in the middle is sort of just the holistic approach to assessing human systems integration with their equipment. You need to take into consideration the equipment, the task, and the soldier for optimal performance. So again, the human sciences, we have the physical anthropology, the human factors, biomechanics, and the cognitive sciences teams, and we use these disciplines to characterize the impacts that the clothing and individual equipment have on soldier and squad performance. So human augmentation. Why would we ever want to consider a wearable device to augment the individual soldier? And the reason why is because the soldiers are carrying a large amount of load, up to 120 pounds, and a large percentage of their body mass, which leads to acute injuries as well as the long-term overuse musculoskeletal injuries. So with that in mind, back in 2001, DARPA initiated a program, Exoskeletons for Human Performance Augmentation. And since that time, there have been numerous systems that have purported to augment the soldier in one way or another, whether it's transferring the vertical component of the load down through the device to the ground and trying to augment load carriage, or whether it's to generate electricity using the human movement so that they can carry less batteries. The one thing that is missing from a majority of these technologies is the impacts it has on soldier movement, use, and performance. A lot of these systems look pretty, but when you put them on, they don't work as intended. So it's our understanding and our goal, and NSRDEC as well as ARL, the Army Research Labs, is to understand and characterize the biomechanical, the physiological, and the human factors implications of these devices before they're put on soldiers and fielded. So NSRDEC has been involved really since 2001 with the DARPA project. We've been involved as subject matter experts. We've been involved with characterizing the impacts of the biomechanical, physiological, and human factors impacts of wearing these types of devices, and we've also been involved with looking at promising devices and then further funding the development of those devices. And over the course of the years, we've really learned a lot about the difficulties of trying to augment a healthy individual with a wearable device. We've had roundtable discussions where in 2015 we brought industry, we brought academia, and we brought government experts all together to look at the gaps and where we need to go to further the science along. And with that in mind, we sort of took a step back from what it was in previous years. It was more of an engineering feat. Let's develop this device and then let's put it on a human. Whereas now the science is more looking at the human, how do we best augment the human and develop the device in concert with that human? so that you can actually start to see some gains of improvement of performance. And there are 3 groups out there right now, Carnegie Mellon, MIT, as well as what's the third? Visa Institute, and Visa is part of the DARPA Warrior Web Project, where they're actually starting to see reductions of metabolic costs while wearing their devices. They may be small, but it's a step forward. We've never seen that before. In the past, it was always cost more energy to use the device than to not use it. So advances are being made. So what does success look like? It really kind of depends on the task. What task is it intended to use? If it's to the left, I think it's to your left, yeah, the high mobility type tasks, it needs to have control algorithms that basically understand your intentions. Otherwise, it's going to be delayed and it's going to cause more effort to use the device than it's going to help. So, and then you have to take into account, okay, if it's more of a fob type task or a logistic type task where you're lifting heavy boxes, the requirements are going to be different. They're going to be more lenient. You don't need to maybe perform in a certain environment, and potentially you could have more batteries available. You can swap those out so the battery life doesn't have to be as long, etc. So it really depends on what these tasks are intended to do. I meant what these devices are intended to do. So this is just an example of us testing a load carriage device. So the first one is a soldier carrying about 80 pounds of gear. So this is the same load. The soldiers are carrying the same load. The only thing different is he's wearing the device. Obviously, that device, as you can see, has a load itself. I think the device was 86 pounds itself. This is walking at a 6% grade. And don't tell the IRB, I was not spotting the guy in the top one. I was supposed to be. But you can see how difficult it is at a 6% grade trying to carry this backpack. And what this device was intended to do was transfer the vertical component of the load down through the exoskeleton leg and to the ground. And it actually did that really well. However, the individual still had to deal with the moment of inertia of that device and accelerate the device forward. It did provide assistance at the hip, but to control the device, you still had to use your own musculature and power. So that's just one example. So how do we usually go through and test the efficacy of these devices? Initially, we usually perform fit and sizing to assess what body types and sizes do these devices accommodate. And then we do a repeated measures design. So we'll have you participate with and without the device doing the same exact task. And some tasks are mentioned below, walking at control speeds, different level grades, for a specific time. Sometimes we'll look at short sessions of 10 minutes and capture VO2. Other times we're going to assess, can a soldier perform a 2-hour march in this device? And we'll look at energy cost, we'll look at heart rate, ground reaction forces, gait parameters, electromyography to see if muscle firing patterns change, to assess what these devices are doing to the individual and what implications it may have for long-term use. Because at this point, we don't have any devices that we can put out in the field to do a long-term study to see the effects of these devices. We also monitor the device itself. Is it failing? Is it breaking down? The power usage and power production. And one important piece of what we do too is we talk to the soldiers after the studies. We do interviews. We ask them to fill out questionnaires to have them provide their feedback on the device and potentially any mission or task that they think is relevant within their MOS. So this is, again, a lot of words, and I don't want to read all that, but there are certain device considerations that we've learned over the past 15 years of what the engineers need to take into consideration. Inertial properties is one of them. Another one is, this is kind of obvious, but it should reduce the metabolic cost and reduce the muscular fatigue as opposed to increase it. And they really have to be cognizant of measuring these types of human outputs to see if their device is actually working. Safety mechanisms too, hard stops, so joints aren't hyperextended, and what happens if the device breaks down? Can you move in it? Does it seize up? These type of things have to be considered. And then the military-specific design criteria. There's a large difference in population. Does the device fit everybody? Who is the device intended for? And can you perform your basic military tasks within this? Again, these are all going to differ on what the task or what the intended use of the system is. Like I said, the high mobility type system is going to be much more sophisticated in terms of control and movement as opposed to a strength task where you just use it to lift boxes and things like that. One of the other important pieces too is the training and maintenance. How long does it take to train up a user? We've had guys in studies for 2 weeks, and even at the end of 2 weeks they're not comfortable wearing the device. So what is that training time? And every individual is different. We've had soldiers come in who just, this is great, put it on and they can go. And then soldiers who are really hesitant within the device and start fighting the device. So that's an important question as well. So after the roundtable in 2015, I think it still stands as the current view is that human augmentation is broad. As we've heard today, you can be drugs, it can be food, it can be wearing exoskeletons. And even within the exoskeleton or the wearable community, many of these devices, or what you call them, are numerous things. Is it personal augmentation? Is it wearables? Is it human augmentation? Everybody has a different understanding of what those definitions are. So we need to decide upon a common terminology for that. The technical challenges really depend on what the intended use of the system is for, and a lot of it is the control strategies and the user interface and how you transfer the force from the device to the person to provide that assistance. And then the human factors in kinesiology and physiology in combination with the engineering of the devices. It needs to be a holistic approach to have these devices be successful. And as I've stated before, that the initial success will come in these niche applications where it's designed specifically to assist with one movement. So where do we go from here? Again, sorry for the lots of words. But it's really to determine the performance requirements, where these devices would be used in military operations, and to develop a collaborative approach between engineers, the human sciences, and the user community to identify the needs and the requirements of these devices. And which joints do we actuate? How much, when is the timing and the amount of actuation for each joint? Trying to understand more of the fundamental human sciences of trying to augment an individual is where we need to go if we ever want to see that high mobility type task. Develop control strategies that detect user intention is extremely important, because if the device moves against you, you're going to increase the amount of work needed to perform a task, which is going to raise metabolic cost. Soldiers aren't going to wear it. Even if it transfers the vertical component of the load, so it may help potentially with injury in one regard, it may create injuries in other areas. So all of these things need to be studied and assessed, and looking at the long-term implications of using these types of devices concerning injuries and concerning the prescribed use. That balancing act between reducing the likelihood of injury and maintaining strength to perform the task. Because the devices could break. You may not be able to use the device in a specific mission, but you still have to have the physical strength to perform the task that you do.